Swayam Prabha. Digital India. Educated India.
So, welcome to the class today, and today's class is going to be completely mathematical. I mean, it's not that earlier classes were not mathematical, but today's class will be only mathematical and nothing else. Okay. Just want to establish a few things and explain to you how we can solve some creeping flow problems. So, so consider, first I am going to talk about Cartesian coordinates. If you remember, I am looking at two-dimensional flows. Okay. We defined stream function and vorticity earlier. We did it, the definition of the stream function using some concept saying it is a function along a streamline which is a constant. Okay. But now I want to say, given a stream function, how can I get the velocity field mathematically? So, consider a 2D flow in xy plane. That means there are two velocity components, okay, and we write the velocity v vector as curl of psi k ek. So, basically I am looking at a vector whose kth component, the flow is the xy direction, so there is no flow in the z direction, okay, and ek is the unit vector in the z direction. So, if I write, I want to calculate what this is. This is, I mean, since you know how to calculate curl, you just write I, j, k, curl is in Cartesian coordinates. This is the gradient operator, okay, and psi has only the third component. Psi does not have the first and the second component. It is only only the z component is there. So, I have 0, 0, psi. Okay. So, if you calculate the curl, which means you are calculating the determinant of this. The determinant of this turns out to be I multiplied by dou psi by dou y minus dou psi by dou x j. Okay, that is the determinant. So, basically this is I unit vector in x direction. So, this is Vx I plus Vy j, and we say Vx is minus d psi by dy, or Vx is plus d psi by dy, Vy is minus d psi by dx. Okay. So, this is your velocity vector. So, what I am saying is, if I give you a stream function in two directions, I mean in a 2D flow, then you can construct mathematically what the velocity field is using v equal to curl of psi and treat psi as a component of a unit vector in the third direction, and the direction where you do not have the flow. Okay. So, and this is exactly what how we defined stream function earlier when we are looking at it physically. Okay. So, now I want to look at omega, the vorticity. The vorticity is, how is omega defined? It is defined as curl of v. Okay, that is the definition of vorticity. and this is again going to be I j k d by dx d by dy d by dz, and velocity is in terms of stream functions Vx is d psi by dy and minus d psi by dx 0. Is this clear? So, velocity we already calculated in terms of the stream functions d psi by dy, and this is minus d psi by dx. So, what is the vorticity going to be now? Remember, there is no change in the z direction because the 2-dimensional flow, nothing is happening in the third direction z, there are no changes in the z direction. Okay? So, d by dz of all these will also be 0. So, this is going to be I am just doing the determinant 0, this is also 0, minus j 0 plus k times minus d square psi by dx squared minus d square psi by dy squared. Okay, just the determinant. So, what I am trying to tell you is this is nothing but minus del square psi. This is what we derive. Okay. And vorticity is basically a vector, and the direction of the vector when you have a 2D flow in xy is in the z direction. Clearly, curl of V is a vector, okay, and I did not emphasize this too much earlier, but I am telling you now curl of V is a vector, xy plane flow vector, vorticity is in the z direction, and this is the relationship between omega and minus del square psi. Okay. Now, for creeping flow, which means very low Reynolds numbers, okay. You will have and 2D flows, you will have curl of omega is 0. This is a condition, okay. Now, okay, what we saw here is V is curl of psi, okay. So, V, remember, when V is written as curl of psi ek, and V is written as curl of psi ek, then curl of psi ek is del square psi with a minus sign, okay. So, I am saying that the stream function velocity is written in terms of the stream function, and this is in terms of psi ek, I get minus del square psi. So, and omega also has a vector in the k direction, okay. So, what is curl of omega going to be? Omega is nothing but omega is minus del square psi, curl of minus del square psi ek, unit vector in the k direction, and curl of, when this unit vector is in the k direction, this curl is going to be again give you one more del squared, one more minus del squared, okay. So, I am going to write this as this is minus del square operating on minus del square psi, okay, ek. So, this is basically del power 4 psi, and so the point I am trying to make here is for creeping flow one can just solve for del power 4 psi equal to 0, where del, so you have to look at this del square like an operator, okay. So this del square, so basically when I am doing curl of V, V is curl of psi, is operating on psi. So curl of V, curl of psi is nothing but minus del square psi, it is operating on psi. Here I have curl of omega, this curl of also gives me minus del squared, because this omega is also pointing in the z direction, okay. So I can use the same idea, if this is not pointing in the z direction, I may get some different result. So because this psi is in the unit direction, the k, omega is also in k, so this curl of omega is nothing but minus del square omega, minus del square of minus del square psi gives you this, okay. This is also, I can write this as minus del square omega ek. So basically what I am doing is saying curl of something, at least in Cartesian coordinates this is del squared. So let me make one thing very clear, this del square is the same as the Laplacian that we have, d square by dx square plus d square by dy square, okay. This is true for Cartesian coordinates. So here del square is d square by dx square plus d square by dy square, okay. So if you want to solve a 2D creeping flow problem, what I would do is I would solve d square by dx square plus d square by dy square squared psi equal to 0, subject to boundary conditions. This is basically this operator operating on psi, again this operator operating on psi, okay. Basically you get a fourth order equation. Now what I want to do is I want to move from Cartesian coordinates to cylindrical coordinates, okay. And basically we are going to do the same thing, and idea is that when you want to calculate the curl in cylindrical coordinates, some extra terms come, and that comes because the derivative of the unit vectors in the theta direction is non-zero, okay. We saw that earlier and I just want to explain that. So I am going to do it for cylindrical coordinates and explain the process. So whatever we did for rectangular Cartesian, I am going to move on to cylindrical. So creeping flows in cylindrical coordinates, okay. So I am going to look at 2D flow in the r theta plane, okay. And I want to calculate what is curl of V first. So what is curl of V going to be? Curl is my gradient operator, which is ER d by dr plus E theta by d by r d theta plus Ez d by dz, okay. Curl cross product with what? V is VR ER plus V theta E theta, okay. I basically you are very comfortable with the curl in Cartesian coordinates, so I just wrote it down. What I am trying to get at is what is going to be the matrix representation for the curl in cylindrical coordinates. That is what I am trying to get at, okay. So how can I write this as a matrix? That is the question. So I have just expanded del, I have expanded V, because this is a 2D flow in r theta plane, okay. And I am trying to now see how to get in terms of the matrix. So If you have A cross B plus C, this is the same as A cross B plus A cross C. Okay, I mean this is an A, B and C are all vectors. So now I am going to write this as this crossed with those two. Okay. I need to let me put the Vz Ez also, because Vz Ez. Yeah. Although it's a 2D flow. Let me put that third thing, so to make it general. So this I am going to write this as 3 terms, ER crossed with this plus this crossed, second term crossed with that plus third term crossed with this. Okay. So ER d by dr crossed with VR ER plus V theta E theta plus Vz Ez. Okay. I am doing one term at a time, and this is going to be, I am going to take the derivative inside here, this ER crossed with derivative of VR with R ER plus derivative of V theta with R E theta plus derivative of Vz with R Ez. So you should use the product rule, but when you change R, E theta, ER and Ez don't change. So they are treated as constant. Okay. So because ER, E theta, Ez don't change, only these guys can change with R, and the derivative is only here. So this is, what is ER crossed with ER? That's going to be 0. Okay. And before I proceed, I want to just mention in the coordinate system, you have I, J, K for Cartesian. What do we write? I cross J is K, J cross K is I, and K cross I is J. Do it in a cyclic way. Okay? Just go cyclic. I cross J gives you K, J cross K gives you I, K cross I gives J. Similarly, when you have ER, E theta, Ez, ER crossed with E theta gives you Ez, E theta crossed with Ez gives you ER, Ez crossed with ER gives you E theta. Okay? So that's how the cross products work, because these vectors are orthogonal to each other. The unit vectors are all orthogonal to each other. So now when I do this, ER crossed with ER is 0, ER crossed with E theta is going to be, what is this going to be equal to? This gives me ER crossed with E theta, Ez, dV theta by dr. Okay. And ER crossed with Ez is, ER crossed with Ez will be minus of E theta, dVz by dr. So basically only when I cross this with this vector, only 2 terms arise. Okay. Ez dV theta by dr. I am just writing this down here because I am going to need this later on. E theta dVz by dr, and I hope I am copying all these things properly. Okay. So now I am going to go to the third term, because this one will have an extra term coming. So maybe I should do the second term. Let us do the second term. So what is E theta d by d theta crossed with these 3 guys, VR, ER, V theta, E theta, Vz, Ez. Take the derivative inside. Okay. So I have E theta crossed with dVr by d theta times ER, dVr by d theta times ER plus VR times dER by d theta. I am just using the product rule, okay, plus derivative with respect to theta. I think I missed an R here. I missed an R. This R is important, huh? I keep the R outside. I keep the R outside, yeah. Plus again product rule. dV theta by dr, dV theta by d theta. I need to dV theta by d theta, E theta plus V theta times dE theta by dr, plus d by dz theta of Vz Ez plus Vz dEz by d theta. Okay. So, all I am doing is I have just used the definition of curl. This is the vector in 3 dimensions, this is a vector in 3 dimensions, and I am just using the definition. Okay. So, I get 6 terms because of the product rule. Now, when theta changes, the unit vector in the z direction does not change, it is always in the z direction. So, this goes to 0 since Ez is independent of theta. Okay. E theta crossed with ER, what is that going to be? That is going to be minus Ez, right? ER crossed E theta is Ez, so E theta crossed with ER is going to be minus Ez. So, the first term gives me minus Ez dVr by d theta, that is the first term. I keep missing the R. So, this is this term, okay. What is this going to be? What is dr by d theta? If you remember what we did earlier, dr by d theta is E theta, okay. Dr by this is E theta, and E theta crossed with E theta will be 0. So, this does not contribute. Why? Because E theta crossed with E theta is 0. This also does not contribute for the same reason. E theta crossed with E theta is 0. And what is d E theta by d theta? E theta by d E theta is minus ER. This is minus ER. This derivative is minus ER. So, this is E theta crossed with ER is minus Ez. Okay. So, E theta crossed, but E theta, so this is going to give me plus I just put an R in front of all the d thetas, man. Oh no, wait. This is okay as it is. I have to put the R here now because the R is here outside, sorry. Yeah. So, this is going to be V theta by R. Yeah. No, don't put any extra R unnecessarily. So, V theta by R minus ER, E theta cross ER is minus Ez. So, this will be plus Ez. Okay. And I have one more term here, dVz by d theta Ez. Everything is Ez, is it? No. This is E theta crossed Ez. What is E theta crossed Ez? It is ER. E theta crossed with Ez is ER. Okay. So, this theta crossed with Ez will give me Er, and I have dVz by r d theta. This comes from this term, E theta crossed with r is minus Ez, E theta crossed with minus Er is plus Ez, I get V theta by r. Okay. This is great. I have 3 terms here. Again, I get this extra term because of this derivative, which is non-zero for the unit vector with respect to theta. And now the third term is much easier because I don't have any of these will change, go in the z direction, the unit vectors don't change. So, I have only 3 contributions. Okay. So, I will just do the 3 things first. So, Ez d by dz crossed with this guy Vr Er plus V theta E theta plus Vz Ez turns out to be dVr by dz. Ez crossed with Er is E theta, and Ez crossed with E theta is minus Vr. So, minus V theta by r by minus V theta. No. dV theta by dz. Yeah. Ez cross with theta will be Er. Yeah. How do I get this? I mean, you can do this peacefully in your room or wherever, and just remember, I am just doing differentiation and using basic cross product. Okay? And this is because now the derivatives of the unit vectors are 0. So, I don't this all these unit vectors can be treated like a constant. So, I get Er Ez crossed with Er is E theta. Is that right? Yeah, Ez cross with Er is E theta, r theta z, z cross with r is theta, correct. And Ez cross with E theta will be minus. That is what I get. Okay. Great. So, I basically have 6 terms, man. I have 7 terms. Okay. The point I am trying to make here is, if I want to do curl of V, I am going to take all the terms with Er together. Which are the terms with Er? I have one term here, dVz by r d theta, minus dV theta by dz. I am just, so I have totally 7 terms. I have, this is 3, this is the first one, and this one. I am adding all the 3, okay. Plus E theta, oh, Joe. I erased this. You have to tell me what this is. E theta, what are the E theta terms? I hope you copied it, huh? What are the E theta terms? As one here, minus dVz by dr. What was the term erased with E theta? Dou? Dou Vr upon dou z. Thank you. I hope it is right. Okay. Plus Ez. Ez is dV theta by dr minus dVz by r d theta plus V theta by r. Okay. I have just rearranged all the terms. The point I am trying to make here is, I wanted to get see, I did all of this. I'm saying this is curl of V. And I'm going to say that this can be represented in matrix form. This can be represented in matrix form as ER by R, E theta, Ez by R, d by dr, d by d theta, d by dz. So, curl of V, this is the matrix representation, okay, is VR R V theta and Vz. I just saw this thing before I came to the class. I hope I remember it right. So, I think this is correct, okay. Point is, if you found the determinant of this matrix, you will get this, okay. So, what I have done is when you go and look at any of these books in transport phenomena, you will see curl of V in cylindrical coordinates. They would have given you a matrix representation. How do you know this? How did this matrix representation come? This matrix representation came by doing what I just did. Take curl using the definition of del operator, use the definition of the V operator and do it term by term. Remember, derivatives can change with coordinates, use all of that, okay. Then you get this expression. This expression is the same as this. Now, that I am going to leave it to you to do, because this is a matrix, this is just a determinant calculation, okay. This is straightforward. So, what I have done is told you how to derive this for cylindrical coordinates. What I want you to do is do the same thing for spherical coordinates. I am not going to do it, but I mean, you can look and you can follow the same procedure for spherical coordinates. Again, the curl operator is given in spherical coordinates, you can do it, okay. So, now let us move on. There is one point I want to make. I want to go back and derive the creeping flow equation again, okay. So, in the r theta plane, if I have, I am going to define curl of psi Ez, because that is how I did it for the Cartesian coordinates. Remember, velocity was curl of psi unit vector in the z. I am doing the same thing. So, my flow is in the r theta plane. I am saying psi is a component of the unit vector in the z direction, in the third direction. R theta plane flow, third direction is z, okay. So, this is equal to V, okay. This is VR ER plus V theta E theta, and I am going to use this matrix representation for calculating the curl. So, what is this? What is curl of psi? ER by R, E theta, Ez by R, d by dr, d by d theta, d by dz, and 0 0, because the vector has only the third component, okay. So, curl is, I mean, I am telling you that this expression here is equivalent to this matrix, okay. So, that is what we have done. And now you can calculate this. What will you get? No changes in the z direction. So, all these derivatives will be 0. So, I only have Ez, only the z component will be there. Oh, no. This is not correct. So, this is ER by R times d psi by d theta minus E theta times d psi by dr plus Ez will be 0. Yeah, sorry, I am just going one step ahead. So, in cylindrical coordinates, how do you find the velocity? In the cylindrical coordinates, Vr is defined as d psi by r d theta, and v theta is defined as minus d psi by dr. I am comparing these coefficients. Okay. So basically this is how stream function, this is how psi is defined in cylindrical coordinates. So I mean, see, physically I explained to you how stream function was defined earlier. Now I am explaining to you, I use that, from there I went to mathematics in Cartesian. I am using the same mathematics to derive things in cylindrical now. Okay. So that is how the mathematics helps you go from one coordinate system to another. Now I want to find out omega. Oh, let me be careful. Omega is defined as curl of V, correct? That is the definition of omega, vorticity. And I am going to write this again in matrix form, ER by R, E theta, Ez by R, okay? Same thing, I am just, because I told you this is the way the curl is defined. Now VR, I am going to write it in terms of stream function. VR is d psi by r d theta. Okay, and v theta is minus d psi by dr, but I do not write just v theta, I have to write r times d theta. Okay, so I have to multiply this by r. I have already found the velocity field in terms of stream function. I am now saying curl of V is, I mean curl is defined in cylindrical coordinates like this. How did I get these magical things r? By going to the definition of the curl and then matching. Okay, so some guy did it, I have just copied it. You just verify that what I have copied is correct. Okay, now let us proceed. So what is curl of V? What is omega? Do this thing. There are no changes in the z direction because it's a 2D flow, right? So it's going to be, yeah, ER component will be 0, E theta component will be 0. Is this clear? ER is going to be multiplied by 0 minus E theta will be multiplied by 0 because ER d by d theta of 0 0, and nothing changes in the z direction. D by d theta of 0 0, so only Ez is going to contribute, plus Ez times, there is also an r there. Okay, I keep the r, d by dr of r d psi by dr with a minus sign. Okay, minus 1 by r d square psi by d theta squared. It is just calculating the derivative, the determinant, sorry, and this turns out to be Ez with a minus sign. I will take the minus out. I get 1 by r d by dr of r d psi by dr plus 1 by r squared d square psi by d theta squared. And this is nothing but del square psi in cylindrical coordinates. Okay, in 2D. This is nothing but del square psi. So I am getting, so I get del square psi. This is therefore omega, which is curl of V, is minus del square psi, and that again is in the z direction in cylindrical. Okay, and del square in r theta. See, 2D in a cylindrical can be in theta z, r z, anything. I'm looking at r theta. You should be able to extend it to other cases. Okay, del square is 1 by r, d by dr of r, d by dr plus 1 by r square, d square by d theta square. So this is very similar to the operator thing that we spoke about. This is operating. This is like a del square operator. Okay, good. I'm very pleased. I don't think I made any mistakes today. Okay. So if you look at what we did earlier, omega was minus del square psi. Okay. So now if we want to again in creeping flow, curl of omega will be 0. Okay, the left hand side goes to 0, the initial terms don't contribute. So this is what I get, and curl of, and omega is again in the Ez direction. So this is also having only the Ez direction. This curl of curl will also be again give you del squared. Okay, so this is basically saying del squared omega is 0 again, or del power 4 psi equals 0. What have we done so far today is let me summarize what we have done so far. So we started with the definition of curl. Okay, curl is A cross B, okay, and from first principles. And remember, unit vectors can change with directions. Okay, then we expanded the curl wrote in a matrix form. So basically tomorrow, I mean, you look at for spherical coordinates, the curl is defined in another matrix form. How do you get that matrix form? By doing what I did today. Okay, whatever I have done today for cylindrical, you have to do the same thing for spherical. Remember, ER cross E theta, E phi, things like that. Derivative with respect to theta can be non-zero. All of that has to be included. Okay, in matrix form, then use this to find curl of psi, omega, and proceed. So now I have established the background. What I want you to do is clearly, I want you to do whatever I have done today for spherical coordinates. Okay. So all you have to do is look at the book, which will have the del operator, which will have the velocity, and let us keep life simple. Let us say we are looking at two-dimensional flows, okay, in spherical coordinates in r theta direction. In spherical coordinates there are 3 r theta phi. So we are going to say flow is symmetric with respect to phi. Okay. So in spherical coordinates, the 3 coordinates r theta phi. consider 2D flows in r and theta, and phi symmetry, basically d by d phi is 0, v phi is 0. That is a typical thing which comes. So, the problem, and when you do this, you will basically have to tell me what that fourth order operator is. Okay, like I got del power 4 psi equal to 0. Del power 4 psi is not, del square is not what you are going to get. When you do it in spherical coordinates, because, and this is a point I want to emphasize today. A lot of places people use in spherical coordinates del squared as the operator, del square square, and then do the problem that we are going to do tomorrow. Okay. But actually it is not del square, it is what is called E square. There is a subtle difference. So, I am not going to go and do this thing again. You guys can sit to, and derive this in Cartesian, in spherical coordinates. I am going to start from that equation tomorrow and proceed to, the problem that we are going to solve tomorrow is the problem of finding the drag force on a sphere under creeping flow conditions. Okay. Most of you may remember the formula from Stokes, 6 pi mu a something. Okay. So, how do you derive that formula? So, for that we are going to look at, the problem is physically a sphere dropping in still water, some viscosity is there, some velocity is there, and you want to calculate what the drag force is. For that I need to work in the spherical coordinate system. We are looking at creeping flow. Okay. So, basically I will get some operator which in spherical coordinates mates in creeping flow we have, I am going to say, satisfies this equation, and E squared of psi is operating on psi is not equal to del square operating on psi. In Cartesian and cylindrical they are equal, but in spherical they are not, and that is something to do with the coordinate system which I do not want to confuse you by explaining. Okay. But I want you to understand that some people write del square has a certain meaning in spherical, but when they solve the creeping flow problem they use a different del square. How can you have two different del squares for the same coordinate system? So, what we are going to use is we are going to use E squared, because and this is what I want you to derive. Okay. All you have to do is, so what you have to do is find VR V theta in spherical in terms of psi, find this using what we did earlier, curl of V in spherical. So, you just have to do whatever it is, term by term, take the cross product, find curl of V, find the matrix representation. So, these are given in several books in the internet. So, I want you to derive it. So, what I am trying to do is making you confident that when you see something you will be in a position to go ahead and derive that equation. That is I think more important than anything else. So, if you see the curl of V is defined in terms of matrix notation, you have to derive this. Once you derive this, then you can find out omega as minus del square psi. This is not going to be del square, this is going to be E squared. Okay. So, let me tell you what your assignment is. Assignment is find curl of V in spherical coordinates, the way we did it by first principles, and find, I mean most of this is given in the net. So, you just have to look at what is d by d theta of E theta, what is d by d theta of E phi, and use those things like we did. Okay. Write this, find curl of V, write it in matrix form. Once you have it in matrix form, then you can find the velocity in terms of the stream function, then you know how the Vr and V theta are defined in terms of the stream function. Then you find curl of V, that will give you E squared. And once you tell me, so you have to tell me what is E squared tomorrow, because I am going to use your E squared for deriving the drag force on the sphere. So that is the assignment. But I will be nice. I can have 3 people work together to find E squared. And you will submit the E squared tomorrow. Okay? Thank you.